Hey there, Calc student. I thought we might just do an integral today. Just messing around a little bit. I got an integral, y equals 1 over x type of thing. Just going to do a, indefinite integral. So, get it in its integral form, get it all ready to go, move that up as an x to the negative 1 like that. There it is. And then I'd probably, what is that rule? You add 1 to the exponent, you bring down the reciprocal, and you're like, oh yeah, with the plus c on there. Oh, but wait. Oh, Nelly. That isn't good right there. This integral doesn't exist? Say what? Like, I don't know about you, but I've been feeling pretty good lately. Like, I can integrate stuff, so what do you mean this integral doesn't exist? I mean, it's okay. This part, is okay. You could have 3 to the 0 power. That's equal to 1. You can have x to the 0 power. Anything to the 0 power, any real number is 1, so this part seems okay, and I know I love my plus c. It's this part here that's kind of got me freaked out. All right, wait. So maybe we need to just look at this with a graph or something. Let's take a look at a definite integral with a graph. So if I'm doing a definite integral, let me just take a look at what this would be. If I was taking a look at y equals 1 over x. Now, if you're not following my thought train right now, it's because I don't have a train of thought. I'm just done. I don't know what we're doing. I was trying to figure this out. Like, this is messed up. So I hope you're okay following along here. So if I had y equals 0, that would be the HA. I know that you remember what y equals 1 over x looks like. That's your basic inverse relationship, right? Like if x was equal to 1 here, it would pass through 1 comma 1. And if x was negative 1, it would pass through negative 1 comma negative 1. So there's that kind of symmetry and everything, but also the graph would, get next to that asymptote and then come down real pretty like that. And then over here and like, oh, real pretty like that. Okay, so there it is. There's my graph. And I know I couldn't integrate across. Like, I understand the integral from negative 1 to 1 of 1 over x does not exist. Do you see why? Yeah, we got this gaping hole in the middle. How could I ask what the integral is across this major vertical asymptote discontinuity? Yeah, this does not exist. Okay, but what if we just messing around here? We start at 1 or something. I mean, how am I gonna get through this mess up here? What if I integrate from 1 to some other number? I don't know. Let's just go like 1 to 3. I don't know. Let's take the integral 1 to 3. That's got to exist, right? I mean, I can see it exists. Maybe I go to my handy dandy TI 84 for this. There's 1, 2, and 3. All right. Oh, I guess this was 1, wasn't it? Well, anyway, you get my point. There's definitely some area under this from 1 to 3. Actually, would you mind type that in real quick? What is the definite integral of 1 over x from 1 to 3? Like, can you get me that value? Whoa, thanks for that. That was super nice. So you got about 1 point, what'd you say? 1.0098 something? That's kind of weird. So we can definitely take the integral of 1 over x. This is kind of messed up. So what's also kind of weird is, you mean to tell me this was almost exactly 1 square unit? Like just a little bit over 1 square unit? Okay, and I think this is even something I could apply the second fundamental theorem to. I could write this as an area accumulation function. Let's make this f of x is the integral from 1 to x of 1 over x dx. Let's write this way. I mean, I think this is good. All right, so we just realized that f of 3 is about 1.098. That was really close to 1. It's almost like there's got to be some number that if we integrate underneath here, we actually get equal to 1. Can you see what this is? In other words, can you try to figure out what you would integrate, what to put here so that you get 1 over x dx, that this area, this answer equals 1? Can you just try a couple there for me real quick? What was that? So what you're saying is you got it to almost work out when x was about equal to 2.7-ish, 2.7. Some people back there are saying a little larger, a little bit bigger than 2.7. Huh. I wonder what, it seems like 2.7 is familiar. And since we're just messing around, I'm just curious, what would f of e be here? Well, f of e would be the integral from 1 to e of 1 over x dx, right? Okay, so would you calculate that just real quickly? What? Are you being for real right here? So you're saying that's 1. That's not, that it's exactly equal to 1. What? Okay, so now this is getting creepy today. Alright, so I started with an integral, I tried to integrate it, I found out it didn't exist. Then I kind of argued, and I was like, wait, it's got to have area. Now we're down here, and you guys are telling me E gives me the area underneath this to be exactly equal to 1. That f of E equals 1. What the heck? I don't know about you, but right about now I'm going, what? Wait. You put E in, and you got back 1? Hold on a second. What's the natural log of E? The natural log of E is... Now, you're telling me you don't remember the properties of logs? Okay, the natural log and E are inverses. This gives you 1. Okay, this is just getting freakier and freakier. So what you're saying... I'm a little bit freaked out right now, but if I'm not mistaken, we just said natural log of E is 1. F of E was 1. You're telling me that the natural log of x was the same as f of x, which is the same as the definite integral from 1 to x of 1 over x dx? I'm not sure. Okay, enough of that. This is a very important idea, and I'm done kind of horsing around here, and I haven't proved to you guys anything. I just showed you something that is outright kind of cool and kind of weird how this just happens to be the case. There's a reason for it. I'm just definitely haven't explained what that reason is. But I think in not so many words, what you might have just started to realize is that I just showed that the natural log of x is equal to the area under the simple inverse graph if you start at 1. So the amount of area under this graph from 1 to x number is the same as the natural log of x number. Okay? And I still haven't even shared with you how you integrate this thing 1 over x other than to tell you that you can do it with numerical integration on your calculator. So this is definitely some weird stuff, but there's no doubt about it. I'm not lying to you. If I were to find f of 2, I could take the natural log of 2, or I could find the area from 1 to 2 of 1 over x dx, and that would both give me the same output. Like, this output would be the same. So, what I'm giving you here is definitely a fact. It's not a theorem or anything, it's just the way it is. It's a fact. And as long as we kind of ran into this, I think we better take a swift time out since you guys were pausing a little bit back here in some of these questions. We better take a quick time out, and I better ask, what is E? Well, there's a lot of definitions for E, and to be honest with you, we haven't even covered all of them up to this point, and I'm probably not going to cover all of them this year. E and natural log are very closely related. They're inverses of each other. So I want to just go back and reiterate what we learned in pre-calculus. E, it is the perfect constant for continuous compounding things. Okay, so E is irrational. It's an irrational number, where e to the 1 is approximately, let's see, I did have this on my calculator. I know we had 2.718, so 2.7182, you know, and dot, 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 like this value goes on and on forever. Okay, so it is meant to be a base. That's why when you go to type in e to the 1 on your calculator, like it automatically raises it to an exponent. We know that it occurs in nature. This compounding that is happening at every instant occurs in nature. And there's some other things too. Like I always get a kick out of this one. When you think about our compounding interest formula from last year, where it had this 1 over n to the n. And then if we did a t here, we could. But as a value gets really, really large into this equation, okay? So as the number of times a person compounds, if we compound billions of times per second, it really does approach E. Like E is this HA of this expression. So if I let n get huge here, I approach the value of E. So there's lots of different ways of looking at what this E value is. And the one that I'm just beginning to horse around with a little bit is that it is this thing for instantaneous rate of change. Okay, and that very closely connects with calculus, right? Like instantaneous rate of change sounds a little bit to me like calculus. So this can be described by calculus. And that, my friends, is to be continued. So we'll get back to this as we learn a few more properties about logarithms and back to e. So, whew, that was kind of a weird introduction for a unit. And right now you're probably going, what? I mean, depends on who you are, but I don't know if any of this made sense to you. That's great. It was more just kind of horsing around with the value of e and the definite integral of 1 over x, and we found ourselves a bit perplexed more than likely, and ready to review logarithms, exponential functions, their graphs, the limits of them, the properties of logs, and all those good things we learned last year are all going to be relevant in Chapter 5. So this unit today, what we want to do is have a very quick review of logarithms and exponential functions and get our skill set back ready to go before we get back into the calculus of that. So, a review of logarithms. I like to start with the parent graphs. Let's take a look. Remember that a logarithm, I always help you to remember logs are this graph that pass through 1, 0. It's a key point that we use to kind of keep track of it. I also want to always put in the vertical asymptote that happens with logarithms. Whether I'm using log base 2 or log base 5 or the natural log of x, remember the natural log of x is really the same as log base e of x, right? They are the same exact function. All right, so what is the domain of this? Well, remember how this graph looks. If I start down here and I come right up through, woo, starting real tight, and if I can make that graph, and then it hooks off here pretty quickly. Okay, so it does turn maybe even sharper than what I just did right there. I did the best I could, and it passes through 1, 0. So its domain is not including 0, and it's off to infinity. It did include 0 because I have a vertical asymptote there. The range is actually all real numbers, and it has this key point, the base function, the parent function, has a key point at 1, 0. Its equation of its asymptote is x equals 0, the vertical line. And it's this beautiful graph. That's, the basic parent graph, whether I'm graphing log base e or if I'm graphing y equals log base 2 of x, they pretty much look the same. Log base 2 wouldn't turn quite as sharply and would go just a little bit different turn around here. But for the purposes of us graphing, that's about all we need. Now that we're getting into logarithms, you do want to be capable of envisioning and maybe even solving a basic limit by considering a graph. So here's a limit, and I'm not going to give you a bunch of properties of limits dealing with logarithms. I'm just going to tell you, when you're dealing with a limit with logarithms, if you can't do direct substitution, then you should think about the graph, because the graph is probably going to tell you what the value of the limit is. So check this out. I think that this limit says find the limit as x approaches 7 from the left of the natural log of 7 minus x. So from the left would mean I would be finding the limit as x approaches, like if x is 6.999. Think about that in here. If x is 6.999, we'd be taking the natural log of essentially something which is positive and very, 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 very small, right? Well, positive, very small, as you can tell from this graph up here, if I'm evaluating a positive very small number for x, y is going to be negative infinity. Okay, so the way we say this limit fails is that the answer to this would be negative infinity. And I just did that graphically. Okay, now the graphs are going to get a little harder, and what you do is you just reorganize them. This is the graph y equals natural log with a reflection. I got an x minus 2 and then out back a plus 3. So all I did is rewrote it with it in a more familiar form that reveals that this has shifted right 2 and up 3, and that this has caused a vertical reflection. All right, so all that's no big deal. And we know how to take and go ahead and do that. We're just going to think about the parent function and the parent function that we just drew, has the key point at 1, 0, and it hooks off there. Now I'm just expecting this to go right 2 units, so that's going to include the VA. So if my VA was at 0, now it's going to be at x equals 2, because I moved right 2 units. That's really hard on here. So, all right, I have my vertical asymptote, and I would like it when you're doing these, follow the same rules we used last year. Write down the equation. It's x equals 2 is my VA. That's part of the answer. Write down where the key point goes, and then make a pretty decent sketch of the thing. Okay, so where did this all go? So there was a vertical reflection. So it used to look like this. Now it's going to look like this. It's gone right 2 units and up 3. So my key point would have been right 2 units. So 1, 2, and then up 3. 1, 2, 3. And also, it's going to look like the blue graph here because it has this vertical reflection. So if I just don't even graph any helper points, I know it's going to do this. And you can check that on Calc if you want to, but that's a pretty close approximation of this graph up here. Okay, so that's that when it comes to graphing logarithms. You just know the parent function and the way they behave. Okay, well, we got to get used to the properties of logs and get ready to use those along with the calculus of logarithms. So to begin with, I want to remind you some key ideas. First of all, the natural log of 1. What is this natural log function? Maybe I better just step aside and be like, okay, you guys, remember how logarithms work in general? Like if I say what is log base 2 of 8, that's saying what power of 2 gives 8? Well, the third power of 2 gives 8. And so this isn't really any different down here. It's just that it makes sense for the base of e. Now, I could even ask you up here, what is log base 2 of 1? And that'd be like saying, what power of 2 will give you 1? Well, 2 to the 0 power is 1. Okay? And this is the logarithmic form, and the exponential form of this logarithm is 2 to the 0 equals 1. The exponential form of this logarithm is 2 to the 3rd is equal to 8. Okay? So that's by definition. So if I ask you what is the natural log of 1, that's like saying what power of e gives 1, and e to the 0 gives 1. If I say what power of e will give you e to the 1st, that's obviously, e is obviously 1. Okay? And that's just the idea that these are inverses. Natural log and e, basically, bam, bam, they cancel out. So, it follows from this, like I could have written it this way. What is the natural log of e to the 5th? Well, that is 5, because ln and e are inverses of each other. Oh, by the way, it follows then, if they're inverses, that 5 raised up to the, well, I don't want to use 5. 5's better for log base 5. We're really going to concentrate on natural logs today. So I could have said e raised up to the natural log of 7, and I could tell you that e and natural log cancel that direction also, and that is equal to 7. That's the inverse idea. Okay. So here are the real ones that we remember practicing when we expand logarithms from last year, right? If I have multiplication, the natural log of a times b is equal to the natural log of a plus the natural log of b. And that's that. The natural log of a divided by b is the same as the natural log of a minus the natural log of b. And this is all review, so I'm not taking the time out here to review all of these properties, why they work. I'm just giving them back to you. You might remember this one. I always like to do my little Power Rangers dance here and say, power down, Power Rangers. And with logarithms, if you're taking the natural log of something to an exponent, that exponent can come down. So this is n times the natural log of a. Okay? So those are the 3 most commonly used logarithm properties, along with the fact that it's really nice to have a change of base formula. Change of base formula allows us to work with all of the other logarithms of other powers. Like it says that if you have the log base anything of anything, so this is log base 2 of 5, and you want to change its base, you can either use the common log, that would be log base 10, or you can use the natural log, and I'm going to go, this is the same as the natural log of 5 divided by the natural log of 2. You're going to notice I probably prefer the natural log because it is our calculus stronghold. Like, there's a reason today I started with natural log, and you're going to see it fits in with calculus very, very nice, and we're going to use the heck out of it in calculus. So I'm not going to do as much with log base 2 and log base 5 and all those other logarithms as I am with natural log. So I'm going to probably favor natural log a lot with my examples. Okay, so you know the directions that you saw in pre-calc. We got to get used to those because they're very useful in calculus. In fact, some of this process seems a little bit like calculus just in its very nature. Like you're taking exponents and powering down exponents. That feels a little bit like the power rule when you're taking a derivative, right? Okay, so you know what the word condense means. Condense is the idea that we're going to try to write this whole expression as a single logarithm. So that's what we're shooting for here, is a single log, right? Single logarithm. All right, so I can't condense unless I have, so condensing is the idea of I have something with a sum or difference and I combine them back like that. Notice that this sum and difference formulas only work if you have a 1 as a coefficient of your logarithm. Like if I were to have a 2 here, there's no way that this can condense backwards that way. All right, so be on the lookout for that. And in our example, what I guess I'm saying is I probably want to do my condensing before I distribute. If I distribute, I can't really condense. So let's just make that happen. As I'm working from left to right, probably the best way to handle this is think about the first two first. So I have 2/3 and then I got the natural log, and this is a minus, so this will be the division rule. This is the natural log of x minus 1 over top of x plus 2. And then I'm right here. I have this minus the natural log of x minus 2. Cool. All right, so this is the difference rule, so I'll have the natural log of x minus 1 over x plus 2 over x minus 2. And you're like, oh my gosh, that's Jenga. So we should take this and think about this as flipping and timesing. And I still have that 2/3 out front, by the way. And this will equal 2/3 the natural log of x minus 1 over, so what I'm doing here is I'm flipping this up and timesing. So that would be x plus 1 and x minus 2. And I don't care necessarily if we expand this, like if we multiply that trinomial out or stop right there. I really shouldn't stop at this point. I have a coefficient. It's here by multiplication. This is an opportunity to power up. So I am going to power up anytime you have that coefficient. Keep in mind that the 2/3 power here, so if I power that up and I got the 2/3, right? That's exactly the same as having a cube root of this quantity squared. And that's probably what I would see if I looked in an answer key written by some author, is that this is the cubed root of all of this stuff squared. So I have x minus 1 over x plus 1, x minus 2, and like that, and like that, and like that, squared. Got it. All right, so it's all there, and that is fully condensed. So there's condense and there's expand and there's simplify. And I'm not really doing that many examples today, but I'm getting you back in the mojo here. So I see multiplication. Let's see what we can do with it. So if I'm going to expand, that means I'm going to take multiplication and split that into the natural log of the sum of the two. So natural log of 3 plus the natural log of e squared. Now notice that squared was only on the e. It wasn't on the 3, and that's shown here in this expression also. Hey, these are inverses. I don't even have to power down. Natural log of e squared is just going to be 2. So the answer to this question is the natural log of 3 plus 2. And that is done. By the way, if there's no parentheses, you assume that only the 3 is in that natural log. Like, this is not the natural log of 5. The way it is written is the way it is. That's the answer to the question. Okay, so I hope you've enjoyed this brief introduction to logarithms. As you're graphing tonight, try to show the key point and the main ideas like I showed in the parent function. And just get used to the idea of how you use the properties of logs and condense and expand. Okay, thank you.